This video is going to get you started on your final exam review. So I'll kind of go through the packet that is posted on Canvas, and I'll highlight the formulas that you do need to know, the formulas that will be given you, and that kind of information. A couple general pieces of information. You can actually use a scientific calculator for the whole test. There will be no graphing calculator. Also, the test itself is 47 questions, most of which are multiple choice, with the exception of your open-ended graphing and your systems. And then there's those problems that are worth double the value, which are your systems with 3 variables, where you'll have actually the choice between Gauss Jordan or Gaussian elimination, your rotated graph, and the graph of the polar. Everything else will have equal weight. Okay, so as you go through the packet, it obviously starts with Chapter 6. You're going Chapter 6 through Chapter 10 from your regular book, and then the prerequisite chapter from the calc book. So from this chapter 6 started with law of sines and law of cosines. You're going to get the reference sheet, which is actually on your review assignment. So on the right here is your reference sheet. It does have your unit circle, and then it has the law of cosines for both the angles and the sides. So if you're looking at this section here, this is your law of sines. You do have to know the law of sines formula, your A over sine of A, and B over sine of B, and C over sine of C. Also from this section is the area when you're given side angle side, and this won't be given to you, so you need to know this. Area equals 1/2. In this case, it would be BC sine of A, but it's basically 1/2 of the product of the two sides times the sine of the non-included angle. So that's one that will not be provided for you. You want to make sure you know that. 15 and 16 are word problems dealing with law of sines, so you need to use your law of sines. And then you get into law of cosines. That's on the reference sheet that's going to get given to you. And in that section was, again, the word problems for law of cosines. It was also Heron's formula. This one will be given to you. So I'll give you that S equals A plus B plus C over 2, and that the area equals the square root of S times S minus A times S minus B times S minus C. So that will be right on the test for you. Then we got into vectors, so you need to know the component form, how to find the component form, and the magnitude. If you continue on the next page, you need to know what to do with these vectors when you're adding them, multiplying by a scalar, or doing the combination of the both. You need to know how to sketch a resultant vector. You need to be able to find a unit vector in the same direction when the magnitude is 1, or if it said find a vector in the same direction. With a given magnitude, something like 2. And for that, you'd find the unit vector, and then you would multiply what you get from that by 2. So if you remember, unit vector is the magnitude, or sorry, the component form of that vector over the magnitude of that vector. So in this case, it'd be V. And this is where you'll split it, simplify it, and if you need to rationalize it, you'll rationalize it. Then we got into dot product. So dot product was the first times the first plus the second times the second. So U1 times V1 plus U2 times V2, this times this plus this times this. That's your dot product. It's a single number. 65 and 67 are just applications of that. Order doesn't matter there. So for 67, you can do 4 times U and that times V, or you can do U and V together and then multiply times 4. The order doesn't matter. 69 is the angle between the vectors. This also will be given to you. The cosine of theta equals U dot V over the magnitude of U times the magnitude of v. So this is one of the, in addition to law of sines and cosines, this is one of the ones you have to have a calculator for. 73 is same set of instructions, just given to you in a different form. So if you remember going from ij to component form, you would write the I first, what's in front of the j second, so that'd be 4, 1, and this would be 1, negative 4. And then you'd use the angle between equation to find the angle between. Continuing with 6-4 on the next page, this is orthogonal, parallel, or neither. Orthogonal means that the dot product is equal to 0. The parallel means that the ratio of their change in y over change in x is the same. So if I was looking at u, it's u2 over u1 would equal v2 over v1. That would make those lines parallel, and then obviously the neither is neither. 6-5 is where we talked about complex numbers. So the absolute value of a complex number is just like the magnitude of a vector. It's the square root of a squared plus b squared. And then to get from complex into trig form, so we're trying to go from that ij format into trig form, you want to convert it into component form. So this would be 2, negative 2. And then now that we know the conversion between polar and rectangular, it's kind of similar to that. You're going to find the absolute value of this. You're going to do the square root of a squared plus b squared. And that's going to give you r. And then the trig form would be r times the cosine of theta plus I times the sine of theta. And then also similar to the polar form, you're going to identify theta by using the tangent of theta equals b over a. So in this case, it'd be y over x. And then you'll find the inverse of tangent. You'll pick that angle just like we do with polar, and that will get plugged in for theta. So the r will get replaced with its value, and then the theta will get replaced with its value. So it would look something like 2 cosine pi over 4 plus I sine pi over 4. Next page starts chapter 7. So chapter 7 was all your systems. We did systems of equations with substitution. We did it with elimination. We did it with graphing. So here's elimination. We did it with graphing. Okay. We talked about word problems in this chapter. We talked about demand and supply. So if we wanted to find the equilibrium point, we set these equal to each other and solved. Since they're both equal to P, you can set them equal to each other and solve. The equilibrium was where we needed to know how many units to produce so that they would equal. Then we worked the systems of equation with 3 variables. So in 7.3, we started with these triangle ones where you're going to use back substitution to work your way up. And then we got into the new 1 and new 2 process where you combined 2 equations to cancel out a variable, combine the third equation with either of the initial ones, cancel out the same variable, use substitution or elimination to get down to 1 variable, and then plug it back in. Then we went into partial fraction decomposition. So if you remember, this is where we had our A over one term plus B over the other term. We multiplied each of these by what was missing from the denominator. And then we focused on just the numerators, one at a time, canceling out the A and the B to solve for A and B. And at the end, plugging those values back in for A over B. So if you want to look through the notes back on, again, partial fraction, that was in 7.3. Then we got into matrices to solve. So this is Gaussian elimination with back substitution. This is where you got your diagonal of 1s, 0s below, but the numbers above. And so we took what was there, whatever these values were. We would have used the top line with 3 variables, middle line with 2, and bottom with just 1 variable. Solved for the bottom and worked your way up. That's the back substitution part. And then we did Gauss Jordan. Gauss Jordan was when it was all the 1s and 0s. So ones, diagonal of 1, 0s above and below. And then the 3 numbers were your solution. So on your final, you're actually going to have one problem between these two, and you'll get to choose which way you're going to do it. Then we got into further operations with matrices in 7.5. So this was adding and subtracting, multiplying, or multiplying by a scalar and adding. Remember that this can only be, so it says if possible, they have to be the same dimensions to add or subtract. Meaning number of rows and number of columns have to be the same. Also in 7.5 was your multiplication of matrices. So for these, in order to see if they're possible, you want to write out the dimensions of the matrix. So if I look at 117, this is a 1, 2, 3 row and 2 column. And then look at the dimensions of B. This is a 2 row and 3 column. And the way you check these is the inner two must match. And if they do, the outer two are your results. So this would be a 3 by 3 matrix. And then I would draw my 3 by 3 matrix and use the name of each cell to help you know which ones to multiply. So if this is row 1, column 1, I'm going to multiply row 1, column 1, and put those together. Then I would go to the next one. This would be row 1, column 2. That would go there. Go to the next one. This would be row 1, column 3, and then I'd put it in that spot. And then continue to work your way through. Now row 2, column 1, row 2, column 2, row 2, column 3, and then row 3, column 1, row 3, column 2, row 3, column 3. If the inner two don't match, then you simply say that it can't be done. Okay, 7.6, we got into the inverses of matrices. So for these, we use the shortcut of the determinant, which is that Jesus fish. We said 1 over the determinant gets multiplied in on, if the original is A, B, C, D, then we switch the positions on A and D. So D goes in the top left, A goes on the bottom right, and B and C get negated. So negative B, negative C. So that if you were looking at 130, I would do 1 over the determinant times 3 and negative 3 are going to switch. Negative 5 is going to become positive 5, and positive 2 is going to become negative 2. And then I would multiply it times 3 times a negative 3 minus 2 times negative 5. Or negative 3 plus 10, which would be 1 over 7. And then that's going to get multiplied in on all 4 spots. Going to the next page, we're now looking at 7.7, which is the determinant of the matrix. Again, with a 2 by 2. This is just the determinant part, so this is just the fish part. And of a 3 by 3, this is when we take the first 2 columns and we duplicate them to the right. And then we multiply along the same direction that we would have done the fish. So top left, bottom right, multiply down those diagonals and add that number together. And then work your way back the other way and add those numbers together. And then whatever you get from the blue diagonal, so the first one, the top left, bottom right, you would then subtract from that what you get from the red diagonal, or top right, bottom left. 7.8 was where we applied those determinants. So to get the area of the figure, we do 1/2 the determinant of what's here. So the A, the B, or the X, Y, X, Y, X, Y, and then a column full of 1s. So I'm going to use these coordinate points to put there, fill the last column with 1, and then multiply it by 1/2 at the end after I found the determinant. And this is plus or minus 1/2. I always use the sign that's going to make my answer positive, so you can't have a negative area. In 7.8, we also used it to determine whether the points are collinear. So this is the same thing. You do your X, Y's for all 3. Fill in the 1s at the end. And this time, we're looking for this to be 0. If that's 0, then these 3 points are collinear. And then the last application of the determinants in this chapter was using them to solve using Cramer's rule. So if it's a 2 by 2 matrix or 2 variables, then we know that D can be found by doing the x and the y's. So x1, y1, x2, y2. D sub x, we take out the x's and put in the constants. So it's constant 1 and constant 2, and then y1 and y2. And dy, we take out the y's and put in the constants. So x1 and x2 stay in the first column, but then c1 and c2 fills the second column. And then x is d sub x over d, and y is d sub y over d. And then the last question in this section is solving using Cramer's rule for a 3 by 3. So much like the 2 by 2, we set up our determinants. D would be all the x's, the y's, and the z's. D sub x, you're going to take out the x's and put in the constants. The y's and the z's stay in the same location. D sub y, this time you leave the x's from the original, but you replace the y's with the constants. And D sub z, take out the z's. So the x's stay, the y's stay, and the z's get replaced with the constants. And then your x would be D sub x over D. Y would be D sub y over D. And z would be D sub z over D. Chapter 8 came next, and this was your sequence and series chapter. So we started with the basic sequences where you're just finding the certain number of terms in the sequence. You're going to plug in 1, then 2, then 3, and so on and so forth. Number 7 is recursive. This just means you need the one before it to get to the next one. 9 and 11 are your factorials. So remember, something like 5 factorial is really 5 times 4 times 3 times 2 times 1. 15 is your summation notation. So with these, we start with the number on the bottom and we stop at the number on the top. So I would plug in 1, I would plug in 2, I'd plug in 3, I'd plug in 4, and I'd add them all together at the end. If the number at the bottom was 0, I would start at 0 and work my way up to 4. Remember, this is the upper bound, this is the lower bound. Then we got into arithmetic sequences, and these are the ones in which if you add the same number each time or subtract the same number each time, they are arithmetic, and that change, the number that you're adding or subtracting, is called the common difference. In 31, first 5 terms of the arithmetic sequence, you're basically just taking a sub 1 and adding 4 to it, and then taking that number, adding 4, and so on and so forth. You can also use the equation for the nth term of an arithmetic sequence, which is a sub n equals a sub 1 plus d times n minus 1. You can plug in your a sub 1, you can plug in d, and then you can find the first 5 terms by plugging in 1 and 2 and 3 and 4 and 5. That formula will get you number 37. So a sub n equals a sub 1 plus d times n minus 1. For 39, you're talking about a partial sum. So this is your n over 2 times first number in the series plus last number in the series. That's your partial sum. So I would take 1 and I would plug it in. That's my last. Take 10, plug it in. Or sorry, that's my first. Take 10, plug it in. That's the last. And then if the number on the bottom is 1, then the number at the top is n. So in this case, it'd be 10. If the number on the bottom was 0, let's say, now my n would be 11 because it's one more number. 8-3 was geometric sequences. This is when you're multiplying by the same number each time. The number you're multiplying by is the common ratio. So for something like 49, you just keep multiplying 4 by negative 1/4 to get the next number in the ratio. In 55 and 56, you're finding nth term. So this equation for a geometric sequence is a sub n equals a sub 1 times r to the n minus 1. You'd have to first use these two numbers to find r. So divide -8 by 16. That's going to be your r. Set up your equation and then find the indicated term. You can use the table feature of the graphing utility because you won't have your graphing utility. And then we got into binomial coefficients. So C was the first one that we found. CNR was n factorial over n minus r factorial times r factorial. The number on the left is your n, the number on the right is your r. You can actually disregard 70. And again, ignore the graphing utility because you won't have it. 73 is your binomial expansion. I'm actually going to zoom out so we've got a little bit more room. We're going to eventually come back up and fill in our CNRs, but we want to first take our first term and raise it to the highest power, work its way down. So I'm going to leave a space. I'm going to do a to the 5th, a to the 4th, a to the 3rd, a to the 2nd, a to the 1st, and then the last one wouldn't have an a. And then I'm going to do the opposite with -4b. So -4b, I'm going to start with that to the 0, -4b to the 1st, -4b to the 2nd, -4b to the 3rd, and -4b to the 4th. And then the last one, which I didn't leave the space for, -4b to the 5th. And then the number that gets filled in those spaces is your binomial expansion number, which you can either use your binomial coefficient, the CNR, or you could use your Pascal's triangle. So that was 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And you would want the second number to match the exponent here. So if this is the 5th and this is the row we're using, those are the numbers that would get plugged in here. 1, then 5, then 10, then 10, then 5, then 1. And I would multiply out all these. I would multiply out all these, all of these, all of these. Oops. These and the last ones. Okay, next came 8-5, which was your probability questions. Remember that you were looking for in 8-5, these were your and or. Actually, in 8-5 and 8-6. If it was an or, you were adding, and if it was mutually exclusive or not mutually exclusive, which meant can the same thing happen? So like, can a jack card and a red card, can something be a jack and a red? If they're mutually exclusive, then you're just adding the probability that they'll each happen. So the probability of, let's say, an even plus the probability of an odd. You can't have both an even and an odd. However, if it's not mutually exclusive, then you have to do the probability, let's say it's a jack and a red, that it's a jack plus the probability that it's a red minus the probability that it's a both, so a red jack. When you got into permutations, which was the PNR, this was n factorial over n minus r factorial. This is where order mattered. So if you're trying to arrange something in an order, that's permutation. When you got into distinguishable permutations like 86, you would do the total number of letters, factorial, over the number of how many times a letter repeated. So for, let's say, the letter T, that happens twice, you'd get 2 factorial. The letter E happens twice, you'd get 2 factorial. And then you would just simplify what you could from there. And then when we got into the other kinds of probability, this was your and probability. And for the and, you were looking for things like replacement and non-replacement. So for and, we multiplied. Like, what's the probability of rolling an even on your the first roll and an even on the second roll? And that you would multiply them out. Something like rolling the dice or a randomly generated number, those would be with replacement. Or if you took something out and you put it back, those would all be the same. With non-replacement, this is like if you're moving a sock from a drawer, or you're taking a rock out of a bag, or pulling a number out and keeping that little piece of paper out. And for those are going to alter what's left in the bag. Okay, then came chapter 9, and these are your conics. So we talked about circles. We talked about parabolas. We talked about ellipses and hyperbolas. Hopefully these are kind of fresh in your mind. It hasn't been that long, but you can look back on your notes for chapter 9 for these. Standard form for the circle. X minus h squared plus y minus k squared equals r squared. There were complete the square questions in here. For parabola, we had y minus k squared equals 4px minus h if it was a horizontal parabola, or x minus h squared equals 4p y minus k if it was a vertical parabola. Then we had ellipses. Ellipses were x minus h squared over a squared plus y minus k squared over b squared equals 1 for a horizontal ellipse where it's wider than it is tall. And then y minus k squared over a squared plus x minus h squared over b squared equals 1 for your vertical ellipse. The way we knew which one was A is that it was the larger. And the relationship between the foci, that was c squared equals a squared minus b squared for ellipses. Then we got into hyperbolas. So with a hyperbola, this is x minus h squared over a squared minus y minus k squared over b squared equals 1 for a horizontal ellipse. And then for a vertical ellipse, y minus k squared over a squared minus x minus h squared over b squared equals 1. And the way we knew which one was A was that A was always first this time. So it was the positive variable. And c squared equals a squared plus b squared. And you had asymptotes here. So if it was a horizontal asymptote, it was y equals k plus and minus b over a times x minus h. And for the vertical ones, it's y equals k plus and minus a over b, x minus h. So the only difference is the a over the b or the b over a. We got into classifying the conics. So remember, you're looking at A and C. A was what's in front of the X. C is what's in front of the Y. If A equals C, then it's a circle. If A times C equals 0, then it's a parabola. If A times C is greater than 0, it's an ellipse. And if A times C is less than 0, it's a hyperbola. We got into the rotation of the conics. So what will be given you, well, actually, let me start with what won't be given you. What won't be given you for the rotation is that the cotangent of 2 theta equals A minus C over B. So that won't be given to you. That's how you find the angle. What will be given to you is what X and Y equal. So the X prime cosine theta minus Y prime cosine theta, and the Y X prime sine theta. Oh, this should be sine theta. And then the y is x prime sine theta plus y prime cosine theta. Those will be given to you. So this, not the other two will. 9.4 was your parametric equation. This is where you're plugging in values for t to get your x and your y. And then eliminating the parameter by solving one of these for t, plugging it in the place of the other one, and the result is just a single equation. 83 is where you're given, so remember, these are two separate questions. One is A with this. You get one rectangular and one parametric, where you want to solve the parametric for a variable and then take it and plug it back into the other one. So because x equals t, I would take t and plug it in the place of this x, making it two parametric equations. And then part B is now use this equation with this one and do the same thing. Then we got into polar and rectangular conversion. So remember, this is r theta. If I'm going from polar to rectangular, then I'm doing r times the cosine of theta, comma, y times the sine of theta. This is rectangular to polar. So if I'm going from x, y to r theta, then I'm going to find the tangent of theta as y over x and use the inverse tangent to find theta. And then r squared equals x squared plus y squared to find r. Nine 6 was all the different kinds of graphs. So these are your circles, your lemniscates, your limicons, and your roses. So there's a bunch of different options here for practice. These, you're only going to get one of these graphs, but it's not a bad idea to practice them so you're ready for all of them. 10.1 was your 3D coordinate system. So remember, you're plotting x, y, and z on a coordinate grid. The distance is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So same as your regular distance, just adding an extra point on. Midpoint is just like the midpoint of x and y, except we've got an extra variable. So it's x1 plus x2 divided by 2, y1 plus y2 divided by 2, and z1 plus z2 divided by 2. Then we got to spheres. So the standard form of a sphere, x minus h squared plus y minus k squared. And this time we add on z minus j squared equals r squared. And 17 is just completing the square with an x, a y, and a z. And then chapter P is going to wrap it up. So here's just some questions from P1, 2, 4, and 5 for review. Hopefully this stuff is fresh in your mind. And that's what you can expect for the final exam.